Our last topic in the hydraulic design of natural channels is going to be related to the natural channel planform. How do you lay out the meander of a natural channel? So far we have emphasized the bottom profile and the relative sizes of the various facets. So we're going to look at now the plan view of the natural channel design. We're going to be looking at what's called a sign generated curve. And the original reference for this came from Walter B. Langbein and Luna B. Leopold in 1966, where they discussed river meanders, the theory of minimum variance. And you see this was a professional paper produced by the United States Geological Survey. Langbein and Leopold demonstrated that river meanders can be estimated using what's called a sign generated curve. So let's get some vocabulary here in visualization. A meander arc length, which is not labeled on the diagram, goes from point A all the way around to the equivalent point on B. Now you can start elsewhere. You could start here, for example, at what they're describing as the inflection point and go all the way to the next inflection point over here. But the key thing here is you're working along the length of the meander. Notice then we have the term the meander wavelength, the meander amplitude. You notice this basically goes from the thalweg to the thalweg. And then you have what's called the meander belt width. So you notice that the belt width is the amplitude plus basically the bank full width. So this is called the meander arc length and the meander wavelength. And notice one meander wavelength contains two riffles, two runs, two pools, and two glides if you have a riffle pool system. Sign generated curve. There's two common forms. Phi is equal to omega times the cosine of 2 pi s divided by m sub a, or phi equals omega times the sine of 2 pi s divided by m sub a. This equation with the cosine describes the meander curve where it crosses the mean longitudinal axis. This equation describes the meander curve at the lowest part of the meander amplitude. Now phi is the angle between the meander path and the mean longitudinal axis. Omega is the maximum angle between the meander path and the mean longitudinal axis. S is the distance along the meander path, and m sub a is the total distance along the meander arc length, or the path. We're going to be using the cosine equation, and in the next slide we will discuss what actually is the mean longitudinal axis. So you see, if we were to draw the x-axis here and look at the meander of the stream, if we were to take the average, for example, of these offsets, we would wind up with 0. This is the mean longitudinal axis. Now taking that cosine equation and placing it in a meander wavelength of 600, which is the meander wavelength of 600, and the meander arc length of 720, which is the m sub a, we take 720 divided by 600 and we get 1.2. S then will go anywhere from 0 to 720. Omega, the maximum deviation angle, is 52.46, occurs right when you just start. And then you'll notice it continually changes as you work your way down through the meander path. Now this photograph doesn't actually have a sinuosity of 1.2. It's just representative of a sinuosity that would be approximately 1.2. Now, if you take a meander wavelength of 600 and a meander arc length of 3,000. 3,000 divided by 600 is 5. So you see this has a large sinuosity. It gives a maximum deviation angle of 112.74, which when measured from the mean longitudinal axis, you'll notice is bigger than 90, so it actually is going, if you will, backwards a little bit in the x direction. The photograph here is representative of one of those very sinuous, more than likely a type E channel. Once again, if we were to take the average of all of the deviations from the x-axis, they would be 0, and this is the mean longitudinal axis. Now, how do you generate these points? If we consider the meander path to be a series of short line segments. So you see, our first line segment, we would be traveling a distance along the arc of S1. Then we would travel a total distance for the next step, a distance of S2, but the total distance would be a sum of two line segments. The distance going from 0 to S1, and then the distance going from S1 to S2. At each of these steps, we have a deviation angle of phi. So you can see I have 3 line segments drawn here. And what we need to do is come up with the x and y coordinates for the stream meander. Once we have the x and y coordinates, we can provide that to the surveyor and say, go stake this out in the field so we can construct it. So that's going to be dealing with these types of equations so we can come up with the x and y coordinates. Now if you look, we'll take a look at the first one here. If you know S1 and you're looking for x1 and y1, it's a simple trigonometric relationship that x1 is equal to S1 times the cosine of phi1, and y1 is equal to S1 times the sine of phi1. So let's take a look at these equations. As I mentioned, x1 is S1 times the cosine of phi1. y1 is equal to S1 times the sine of phi1. Now if we go to x2, we basically make x1 and y1 the new origin. So x2 is equal to x1 plus then the difference between S2 and S1, which is the length of that second line segment, and then we multiply by the cosine of the second deviation angle. Now likewise, y2 can be computed the same way. And as you can see, you can step through this where each successive point is calculated from the preceding point using the appropriate deviation angle and the incremental distance that was moved along the arc of the meander. So if we look at Harmon and Starr, for example, for a C4 channel, the meander length ratio, so the total length of the meander divided by the riffle bank full width is supposed to be between 7 and 14. The meander width ratio, the width of the belt divided by the riffle bank full width is supposed to be between 3.5 and 8. The radius of curvature, so the radius of curvature divided by the riffle bank full width is supposed to be between 2 and 3. And the sinuosity for a C4 channel is supposed to be between 1.2 and 1.4. So if we take, let's say we had a bank full width of 26 feet, and I'm going to select a meander arc length ratio of 10. I then calculate the meander arc length as being 260 feet. Now you notice this meander arc length contains 2 riffles, 2 pools, 2 glides, and 2 runs. I'll select a sinuosity of 1.3, and then I will calculate the meander wavelength as being 260 divided by 1.3, or 200 feet. I'll use the equation from Langbein and Leopold that is an approximation for the maximum deviation angle. So it's 2.2 times the square root of the sinuosity minus 1 divided by the sinuosity. So the maximum deviation angle is 1.0568 radians. Now we're going to split the meander arc length into a large number of line segments and determine the x and y coordinates. This I have done in a spreadsheet. So I use the spreadsheet, and I then come up with a meander amplitude of 77 feet, a meander belt width of 103 feet. So then I check my meander belt width ratio. So that comes out to be 103 divided by 26 is 3.96. If I then do the same thing for the radius of curvature, radius of curvature is 54 feet, and the radius of curvature to bankfull width ratio comes out to be 2.08. So if I go back, if I look at the meander belt width ratio and the radius of curvature ratio, so the meander belt width ratio is anywhere from 3.5 to 8. I have 3.96. And the radius curvature ratio comes out to be 2.08, and you'll notice that's between 2 and 3, and I had selected a meander length ratio of 10, and I selected a sinuosity in the range of 1.3. So by selecting these parameters, I should get a design that functions successfully as a C4 channel. Now, how do you lay it out? Well, this is a different meander wavelength and a different meander arc length, so that I could plot this using relatively even numbers. So for this, we'll have a meander wavelength of 320, a meander arc length of 400. 400 divided by 320 gives me a sinuosity of 1.25. I then calculate the maximum deviation angle of being 56.37 degrees. Now for this particular example, I made the riffle, the run, the pool, and the glide all to be equal length, or 25%. So you can see, working along the arc then, I would take the length of the riffle, except that's not the riffle, that's the run. So let's start again. From where I am here, this would be the beginning of the run. So I take the run, and then I would go into the pool. Then I would go into the glide, and I would come out at the riffle. Then I would go into the run, into the pool, the glide, and the riffle. So now I have the x and y coordinates, and I do have an estimate of the radius of curvature. Because this is a fairly constant radius of curvature, you can actually have the surveyors probably stake out the entire length around the pool and the glide using the radius of curvature. So this then would actually be the plan view of the thalweg. Now you can then enhance the diagram to show the bankfull top width and actually produce a set of engineering plans that shows how to construct a stream meander. What we're going to look at next is the spreadsheet that I utilized to generate the sine generated curve.